So I suppose we can start. Yeah.
Okay.
Yeah. So we're very happy to have Alexandre Jollivet from. I'm sorry, I forgot your university.
Of Lille.
University of Lille, and
Yes.
so he graduated from University of Nantes under the supervision of Professor Roman Novikov in 2007. And so he's going to talk on inverse transport problems. So over to you, Alexandre Jollivet.
Okay, so you see my screen?
Yes, I do.
Okay, so let's start. So I will talk about inverse transport problems. So I will mainly, so the lectures are mainly based on what I have done in this inverse transport problems. So first, let me start with motivation. So the motivation comes from imaging, medical imaging. So the propagation of X-rays inside a biological tissue can be modeled by the following transport equation, very simple one. V scalar product with grad x of u xv plus sigma of x u xv equal to 0 for x in xv in the product big X times big V. So big X is so it's just the set the set that models the biological tissue, and V it's just the unit sphere. So in this talk, I will always assume that big X is just a strictly convex bonded open subset of Rn and bigger or equal to 2 with a smooth boundary d of x. And so in this equation, u x of v and v is just denotes. So the physical meaning is just that it is the intensity of the X-rays at which goes through x in direction v, and sigma of x is the absorption parameter of this X-ray inside the medium at the point x. So the light source in case of X-rays, when you do an X-ray scan, so the sources is outside your body. So here the light source, the external light source, is modeled by a function g, which is in some L1 space of the incoming boundary set gamma minus. And so this gamma minus is defined as a pair of boundary points and velocity, so that the velocity times the normal vector of the domain x at the point x is strictly less than 0. And we also define with an opposite sign the outgoing boundary condition gamma plus. So let me show you a picture before. So here you have the light source, which is here. You have I just draw two rays of light. So one which comes from x0, the boundary point x0 in direction v0. So x0, v0 are points in the incoming boundary set, and the propagation of the X-ray is just a straight line, and it hits the boundary at the point x1 in the same direction v0. Sorry, I put v1, but it is v0. And in that case, x1 v0 is in gamma plus. So here, nu of x is the outward normal unit vector at x of at the boundary point X, so it's just this vector here. And the light source sent rays all over the domain. So here you just have 2 rays. So here you easily obtain a solution, explicit solution of this equation, just by integration. So if you consider ux plus tv v, you take the derivative with respect to the parameter t, you have just v grad x of u. And so if you go back to this equation, you replace x by x plus tv, you obtain this equation here. And so it's just a simple ODE that you can find the solution, and it is just given by this solution here. So g of xv, so xv is just an incoming boundary point, exponential minus integral of, from 0 to t of sigma. So the measurements are finally done at the outgoing boundary point x plus tau xv, v, and v. And this is just given by gxv exponential the x-ray minus the x-ray transform of sigma of vx. So the x-ray transform of sigma of vx is the integral of sigma over the straight line which goes through x in direction v. So when you do an X-ray scan, you have light source, you know the intensity which is incoming, you measure what is outgoing. So your data for an X-ray scan are exactly all possible integral of sigma over straight lines. So the question in this X-ray imaging is to recover sigma from the data, the boundary data. And so it means that you have to recover sigma from its X-ray transforms. So this is a linear problem, and it is well known. So it was first studied by Radon, I guess, in 1917. But here I will use a much simpler formalism. So I'm recalling just the central slide theorem in dimension 2, n equal 2, sorry, it's not d, it's n. So it relates the Fourier transform of a function f with the Fourier transform of its X-ray transform. So the formula is given here. The Fourier transform of f at the point, at the moment lambda theta perp is equal to this Fourier transform with respect to the parameter lambda of the X-ray transform of f. So with the following notation. So here you just have it's a very straightforward identity. There is no much to say, and it's already provide you with in inversion formula because you just have to use the inverse Fourier transform and you recover f from p of f. And you have also a stability estimate, so which is that L2 norm of f is equal to some Sobolev to the norm of pf in some Sobolev space of order 1/2. So the norm is written here. So it is a stability. It is what we call a stability estimate because it provides you with a norm on the measure, so that if you have some error, then it reflects some it gives you all the error on the parameter is controlled from the error on the data. So just to finish this motivation in X-ray in medical imaging, I just wanted to give you a classic textbooks on computerized tomography done by Natera in '86. So you can find, I mean, a lot of subjects on it. And so this is this is an inverse transport problem, a very basic one. So where we're trying to recover the optical parameter sigma from the data, which were here the X-ray transform of sigma. So here also one I should say, so here's the light source. Yeah, so you do it for any, okay, so you do it for any G. You collect the data for any G, any straight lines. So now I will jump to another inverse transport problem. So when you deal with lower energy photon, then the propagation is not along straight lines. It's you have to take scattering effect into account. So it will change the equation as follows. So you still have this this first terms, and then you have this modification, which is given by this integral operator, integral over v of kx v prime v u x v prime dv prime. So again, you have the light source G, and here in this in this equation, sigma is again the absorption parameter of the medium at the point x, and kxv prime v is now related to the probability for a photon which comes from which is comes at x from the direction v prime. So it's the probability that such a photon is scattered in the direction v. So in this equation, I will assume that sigma and k are all non-negatives, and I will assume also for the torques that they are bonded. And I will denote the quantity, this following quantity sigma s, and the inverse of this quantity has a physical meaning, which is the mean free path. So I will explain you what it is in the next picture. So sigma s minus 1 is actually the mean free path. It gives you the mean distance that the photon travels before two scattering events. So you see you have one scattering event, and in mean value, this photon will travel a distance sigma s minus 1 in before another scattering. Okay. So again, so this equation and the inverse problems related to this equation we are going to study as application is in optical tomography. So you can find a nice reference here. So if you have any question before I goes on, please ask. I don't know exactly what you know, what you understand, and so it's good if you can ask questions. So in full generality, it's not clear that this equation has a solution, has a unique solution, and so the existence and uniqueness is not granted by this only assumption on sigma and k, so bondedness and positivity. But if you can define an operator, the measurement operator called albedo operator, which sends a light source G to the boundary measurements U restricted to gamma plus, where U is the solution of our linear Boltzmann equation, which is written here. Then the question we are interested in now is, can we recover uniquely sigma and k from the operator, the albedo operator A? And okay. And we will also be interested in the stability question. Can we find two norms, 1 and 2, on the optical parameter and on the albedo operator, so that you have this kind of stability estimates on the optical parameter and the measurement operator. So you have a bond of the difference between two pairs of optical parameters sigma k and sigma tilde and k tilde by some function of a norm of the difference of the measurements operator for sigma k and sigma tilde k tilde. And this function has to satisfy that it goes to 0 as t goes to 0. F of t goes to 0 as t goes to 0. So when f of t just t, we say that we have Lipschitz stability. If f of t is t up to the power alpha, we say it is Holder stability. And then if it's 1 over logarithm, we say some logarithmic stability. So here it's t minus 1, I think. Yeah, there is a minus 1 which is missing here. So we are going to study this problem first in the first part of the talk. And for this, I will treat the forward problem, which is to study the existence, uniqueness of the solution, and the well-posedness of the problem. I mean, to define the albedo operator A. So let me go now to the functional framework. So we introduce the following functional space W. So it consists of functions which are in L1, but better than L1. It's tau L1. So by this, I just mean that tau minus 3 is in L1. And with the following directional derivative also in L1. So I forgot to say, but tau is here the travel time. So tau, if I take a point x in the domain and the direction v, tau x of v is the length of the segment which is contained in x and which goes through x in direction v. So okay. So I will also introduce the travel time tau plus. Tau plus is now the length of the segment which goes from x in direction v until the boundary. So tau plus is just this length here, and tau minus will be the other part, this length here. So tau is actually tau plus plus tau minus. I will use this notation. So let me go back to the functional space. So this functional space is endowed with this following norm. And traces on the boundary are well defined in that space. So if you take a function u in W, any restriction of u on the boundary of x times v is well defined. and you have it is very well defined and continuous. So again, by the method of characteristics, you can transform the stationary linear Boltzmann equation into an integral equation. So it will take the form identity minus t minus 1 ku equal to L of G. So in this equation, L is just a bounded operator from L1 to W. T minus is a bounded operator from L1 to W, and K from to L1 to L1. So, so this is let me okay. So this operator here goes from goes from to L1 to W, and here it goes L goes to L1 to W. And so all the solution, I mean, the existence theory and uniqueness theory for this linear stationary linear Boltzmann equation is reduced to inverting this equation, this operator. So you have explicit formulas for T minus K and L. So they are given by this. So LG is at the point X and V is given by by Gx minus 2 minus XVV. So you are inside the domain here. So, and this point is just the point that, so if you take the line which goes through X in the opposite direction minus V, so this line will hit the boundary at this point here. So LG is given by this. So it is, LG is just the solution of the linear Boltzmann equation without this term. So it was the first equation I have considered before. And K of U is just the right-hand side of the stationary linear Boltzmann equation. And 2 minus is defined as follows. So you can forget about this quantity. I mean, you don't need so these explicit quantities to understand the torque, but it's better if you use. It's better that you see that everything is as an explicit form. And I will also introduce the following factor E plus. So E plus, it's exponential minus the integral over sigma, the integral of sigma over the broken line, the broken segment which goes through X in direction V for the first part, and in direction X, in direction minus V prime for the other part. So now let me state the condition of for a solution to exist to this equation. So if this bounded operator is invertible in this space, then for any light source G, you have a unique solution to our equation. These solutions belong to the space W, and the albedo operator A is well defined. So, and it's, so it takes the boundary, the light source G to U restricted to gamma plus. So this condition is satisfied for classical, for some classical subcritical conditions. So for example, if tau sigma S is strictly less than 1, then you have invertibility of this operator. Or if sigma is bigger or equal to sigma s, then you also have invertibility of this operator. So, so in this talk, I first consider only L1 framework, but you can do also any LP framework, and you can also define the LP framework for any P between 1 and infinity. So, for example, this classical subcritical condition were generalized in LP framework by Egger and Schlottbaum in 2014. So now, yes.
Alexandre, I have a question.
Yeah,
So,
yes, please, please.
The subcritical conditions that you have mentioned, right? So does it imply that that I minus T inverse K, right? That can be expanded into some Nyman series expansion or something like that, or?
Definitely, this is what we are going to do actually.
Oh, I see. Okay, okay. All right.
Yeah, this is what we are going to do. So it's even more. So for your question, so if you have this kind of one of them is satisfied, you have a norm of a certain operator which is strictly less than 1. And in that case, you have the Neumann series is well defined. I mean, it's the series is uniformly convergent and it holds. But in your case, we will just require this invertibility condition, but at the end we will do some kind of Neumann expansion, not for every term, but until a finite number of terms. So I will show you just in few minutes.
Okay, thanks.
So, and this is exactly the next slides. So it's what we call the circular decomposition of the transport of a transport solution. So you take a source like G, then UG under invertibility of this operator, you can rewrite U as a sum of 3 terms. So the first one is okay. I didn't see it. So here G is L. So G is L. Sorry for the misprint. So you have 3 terms. You have L plus T minus 1 KL plus this third term. So everything is well defined through the assumption that it is invertible here. This operator is invertible. And so the first term here, G of G of J of G. So phi is here G. Sorry again for the misprint. So J of G is what we call the ballistic term. T minus K G J G is the single scattering term, and the third term is what we call the multiple scattering term. So G phi is JG is the ballistic term, so it takes into account only photons that didn't undergo any scattering. So they propagate along straight lines. Here's single scattering term. So this is the photon which have undergone only one scattering event. And this last term takes into account only photon that have undergone at least 2 scattering events. So using this decomposition, you have a decomposition for A, which is A0 plus A1 plus A2, and this is given by taking the trace of each terms. So you take the trace at the outgoing boundary condition gamma plus. So, so if you now write the Schwarz kernels of these operators, you obtain the following explicit formula. So Phi is so the distribution kernel of A is given by alpha 0 plus alpha 1 plus alpha 2. Here, d mu is just the canonical measure on the boundary of the domain X. And you have this explicit formula for alpha 0 and alpha 1. So alpha 0, you see that you have, again, the X-ray transform of sigma over the straight line, which goes through X in direction V. And you have two singular distribution, two delta function, a delta function in the velocity space and a delta function in the spatial variable. And then you have a second term alpha 1. So in this first term, you do not have any k. So this is the scattering kernel of the ballistic part of the albedo operator. And alpha 1 is the distribution kernel of the single scattering term of the albedo operator. So it is given by this distribution kernel. So here you see E plus, which I have defined previously, times the scattering kernel K. And again, you have some singular distribution delta. So this is a singular distribution only in dimension greater or equal to 3. I will explain this later. And dimension 2, actually, this is alpha 1 is already a function. And then you have alpha 2, which is the scattering kernel of the multiple scattering part, and it is given by a function which has this kind of regularity. So it is a function which belongs to this space L infinity gamma minus L1 gamma plus dxi. So now we will use this decomposition to recover sigma and k from the albedo operator A. So first, so we applied first we take a light source F epsilon. We apply the difference of measurement operator A and A tilde. And we take a detector C. So it modeled a detector, and you integrate over gamma plus. So you have this decomposition into 3 terms. So so E1 is related to the ballistic term alpha 0, and you have this explicit expression. E2 is related to the single scattering term, and you have this expression here, explicit expression, and I3 is related to the multiple scattering term, and so it's just a function. I3 just see a function and times F epsilon X prime V prime. So and integrate over d mu X prime and dv prime for I3. So I do not write I3 because this is not relevant for what we are going to do. So the picture is as follows. So F epsilon will we will take a boundary point x0 prime with incoming direction v0 prime. So sorry, here it's a plus, it's not a minus. And we will take a light source F epsilon, which will concentrate at x0 prime in direction v0 prime. So our light source will be some kind of, will approximate a delta function in x0 primes times a delta function in v0 prime. And so in that case, if we have a delta function, so the ballistic term will just propagate along straight line, and the support of the ballistic term will be at this exit point. And so if you place a detector here, psi, whose support will be smaller and smaller and concentrated at this point, you will recover actually the only the scattering, the ballistic term. So what I mean is that if you take f epsilon, which will be a delta function at x0 prime v0 prime, and you take psi to be concentrated here, then what you will recover at the limit epsilon goes to 0, and when the support of psi will shrink to this point here. Yeah, I made a mistake here. It's xv. It's not this term does not. You have to delete this term. So it's c xv. So so if the support of c is concentrated at the exit point, you will exactly at the limit recover this quantity here. And for the ballistic term, if you choose a direction v, the support of the photons that undergo only one scattering event that are emitted from x0 prime in direction v0 prime, and they undergo only one scattering event in direction v, so they can only hit the boundary along the intersection of the ball with this the plane with direction v0 prime v and passing through x0 prime. So so the support of this photon at the exit is just given by this line here. And multiple scattering will actually, the support of the multiple scattering will be all over the ball. So if you take a detector of psi, which will concentrate only near the curve, this curve, then you will recover only the single scattering term at the limit. And for the multiple scattering term, which is all over the ball, at the limit, it will be 0 in both cases. So in dimension 2, this scheme does not work because, at least for the scattering kernel, because so the reason is that this curve in dimension 2 has the same measure as all the boundary of the domain. So you cannot distinguish between single scattering term and multiple scattering term by this scheme in dimension 2 in general. So exactly what I said. So you first take f epsilon, which concentrate at x0 prime and v0 prime. You take the limit. You obtain these two quantity. For I3, you have another term, and then you choose appropriately the detector psi, and you obtain the following stability estimates, and you can also say uniqueness results. So this bond, just let me say, this bond comes from the original decomposition here. Psi is a bounded function by say 1. So if you take the absolute value of this term, you can bound this by the operator norm of A minus A tilde.
So Alexander, sorry to interrupt. I have a question. So in two
Yes.
dimensions, there is an obstruction, is it? I didn't quite catch that point. Can you please repeat?
Yes. So the obstruction is that if you have a disk, you agree? And if you have the same picture, the curve here will be a curve on the disk, on the circle. So the measure of this segment on the circle is non-zero, and so you cannot distinguish multiple scattering term and single scattering term because the multiple scattering term, the support of the multiple scattering term at the exit will be the disk, and it will be distributed over the disk, over the circle, sorry, and the single scattering term will be distributed along a part of this circle, but you will have multiple scattering photon and with a non-vanishing intensity. I mean, with intensity of the same order as the single scattering photons at the exit.
I see. So, but is it that that there is really an obstruction to uniqueness, or this method actually gives you that there is an obstruction? So,
I will give you the other examples where you can prove in two dimension uniqueness, but you have to assume you have to add assumption on the scattering kernel K.
I see. Okay. All right. Yeah.
But your question about uniqueness in two dimensions is an open problem. What I'm saying is that this scheme is not working in two dimensions. But I'm not saying that in two dimensions there is a problem. We don't know. It's an open problem.
I see. I see. Okay.
Okay. So at the end, you have this stability estimates, and you can think. So you can think of it as a uniqueness results also. So here the norm between the measurement and A tilde is given in an operator norm. So the usual one, so of bounded operator from L1 gamma minus to L1 gamma plus. And you have a bound of the difference of the exponential of minus the X-ray transform of sigma minus exponential minus the X-ray transform of sigma tilde. So if the measurements are equal, so if you have 0 here, so which means that we are dealing with the uniqueness question, then it means that the X-ray transform of sigma and sigma tilde are equal. So it means that then if you choose any point x0 prime, v0 prime, it means that the X-ray transform of sigma and is equal to the X-ray transform of sigma tilde. And as I said at the very beginning, you can invert the X-ray transform and you obtain that sigma is equal to sigma tilde. And for the other term, when you choose appropriately the detector at the limit, you have this bond of this quantity, E plus K minus E tilde plus K tilde, integrated over the velocity space and over a straight line. And if you have 0 here, it means that E plus K equal to A plus E plus tilde K tilde. And E plus only depends on sigma. So once you have recovered sigma, you know E plus. So it means that then you have equality of K and K tilde. So this estimates or provides you uniqueness, and you have you have even a stability estimates with respect to the measurements, which is given here. So here you have we can put this in a more interesting and a more easier estimate to understand. I mean, here it's a stability estimates for the X-ray transform of sigma and sigma tilde, and we want a stability estimates for with respect to sigma and sigma tilde. So this was our goal. Here we have our first norm on the measurement, but here it's not, though it can be interpreted as stability estimates, and these terms and this term can be interpreted as the norms on the operator on the optical parameter sigma and k. It is not it is not the kind of estimates we were looking for at the beginning. We really wanted a norm on sigma and sigma tilde and a norm on k and k tilde, which are bounded by the norm, a norm on the measurement operator. So to do this, we actually obtain a conditional stability estimate. So here I told you you have you from this estimate you easily see that you can obtain a bond on the difference of the X-ray transform of sigma and sigma tilde, and then if you use Fourier slice theorem, for example, or something else, you can easily see that you obtain this bond for h up to the power 1/2 in Sobolev norm. And so when s equal 1/2, theta, which is given here, is 0. So you obtain a conditional stability if you assume that sigma k has some kind of regularity. So if you assume that sigma is sufficiently regular and k is continuous and bounded, then you have you can, for example, if you have this regularity, you can then interpolate between this estimate here and s equal and the power -1/2 to obtain this interpolation, this stability estimate on the optical parameter sigma. So this is just obtained by, as I said, by inverting the X-ray transform first, and then interpolate with this inequality. So which means that you have a priori knowledge on the smoothness of sigma. And then once you have this estimate, you can use it to put this here, and you obtain this following stability estimate for k, which gives you a stability estimate which is expressed through the L1 norm of k. So when you do this conditional stability, your stability degrades a little bit, because you goes from Lipschitz stability to Holder stability. But it's still okay for an inverse problem. It means that it is a nice inverse problem. It's not it's midly ill-posed. It's okay. It's fine. So what I said in this part, I give you some references, so you can find most of these things in this work of Shuli-Stefanov. So in this work, you have the uniqueness question and the functional framework. In this paper, you have first a stability study, but for particular classes of scattering. Scattering parameters K. And with the work with Guillaume Ball, we deal with more the general form of the scattering kernel. And finally, you have this paper which provides the more even more a more general case. So I don't see. Yes. Okay. So this work deals also with what we call gauge invariance, gauge equivalent classes. So I will talk about this just in a few minutes. And prior to these works, you have also people like you have also people who have worked on this kind of problem. I'm thinking of Vladimir Romanov in 1994, and also Bondarenko in also in the 90s. So as I told you, here we have played with the singular decomposition of a transport solution, and we have used that ballistic term is always more singular than single scattering term, which is, and the single scattering term is also more singular than the multiple scattering term, provided that we are in dimension equal or greater than 3. But so our in dimension 2, so in dimension 2, if you just look at the recovery of sigma, it still works. So everything I said before is working for sigma in dimension 2. But in dimension 2 for the scattering kernel, as I said, it is an open problem. However, you can have, in certain cases, uniqueness and stability. So, for example, in this work of Damasan in 2002, he is able to obtain uniqueness in dimension 2 when he considers only isotropic scattering kernel here. You also have a uniqueness for other classes of scattering kernel, I think, but still it's just a special forms. And the funny thing is that so first you recover sigma as usual, and then for K, he is able to he use an inversion of an attenuated Radon transform, X-ray transform, to recover K in a single measurement. So this is a first result in dimension 2. In dimension 2, you have also work by Stefanov and Ullman under the assumptions that K is small, so K bonded and small. In that case, we are able to separate the single scattering from the multiple scattering, and then to recover the scattering kernel K. And so here you see that in our setting we have a lot of measurements, and we have a lot of sources, and all of them are spatially and angularly resolved. So it means that we have a lot of data, which in practice is not clear to have. I mean, it's not clear that it is reasonable from the practical point of view. And but if you want just to recover sigma when you have a scattering kernel K, then you don't need to use singular sources, as I said. You can use I mean, our singular sources was a delta function in space and velocity. But for example, in this work, if you use just a singularity, which will be just a jump in values, a small jump like you can think of the EV side function, then it is enough to consider such kind of singularity to recover sigma in presence of K. So now another comment is what we call a gauge invariance. So when sigma is not anymore isotropic, so sigma may depend on V now, then you obtain that the albedo operator for sigma and K is equal to the albedo operator of sigma tilde K tilde, where sigma tilde and K tilde are defined through this formula. So in this work, they interpret these stability estimates as stability estimates for gauge equivalent classes. So these estimates are truly stability estimates when you consider gauge equivalent classes. And my final remark will be about solvability conditions. So I gave you these two classical subcritical conditions, but if you use some compactness property, then you see that the value so if you use some compactness property of this operator, then you see that it will be so if you put a lambda, for example, for lambda, it's just somehow you just rescaling the scattering kernel. So we think of it as putting a lambda here. So he minus lambda, this operator will be invertible except for a countable number value of lambda, just by a compactness property of t minus 1k. And so this you can do it, for instance, in LP framework. So in that case, under this assumption that K has this belong to this space, then you can prove that this operator is a compact operator in this space. So here I just put the L1 framework, but you can define the LP framework. So and under this assumption, it means that your solvability condition is satisfied for any lambda K for except for a countable value of lambda. So it is it shows you that the invertibility, the lack of invertibility are satisfied only for specific value of the parameter K. So in general, somehow under some additional property of the scattering kernel K, then you have uniqueness and existence of the solution. But you have to use to have an assumption on K so that you have a compactness property that you can use. So now I wanted to introduce the time dependent analog. So the idea was to use time to obtain So in the stationary case, we were not able to recover k in dimension 2 with our scheme. But now, if you assume that we have time measurements and time sources, then we will use time to recover k even in dimension 2. So for this, we consider the following time-dependent linear Boltzmann equation, which is given right here, and with the following initial and boundary conditions. So at time 0, the domain is not illuminated, so u equal to 0 inside the domain, and at a positive time between 0 and t, you have an external light source phi, which belongs to this space. And we will assume that the support of phi in time is inside the segment 0 eta. So at the very end, phi will be a product of a function of xv and times a function on the of the time t, and the part which will only depend on t will be a delta function near 0. So at the very end, we can take eta as small as we want, and we will use this kind of external light source. So the functional framework here is given by the following space. So you consider this space here. So function u, which are in L1, with the following derivative dt plus v grad x u in L1, and also with the following condition, boundary condition in initial condition in L1. So you can rewrite this equation in the framework of continuous semigroup. So you have so let me first skip this part. So the solution u for our equation. So the equation will admit a unique solution u, which is given by this formula. So G minus is just this operator, and this is the solution of our linear non-stationary linear Boltzmann equation without this term. And U is a semigroup generated by this operator T, which is T1 plus K. So yes, so T has nothing to do with our T in the first part. Actually, the first T in the first part, I had written T minus 1. It should have been written T1 minus 1. So U is just a semigroup generated by this operator T, and K is is the same operator as in the first part. So it's the integral operator. Is the operator with the with the integral operator with kernel little k. So for this equation, you do not need a subcritical condition. The solution always exists. You do not have this kind of subcritical condition, and the link between this equation and the non-stationary linear Boltzmann equation and the stationary linear Boltzmann equation is if you integrate over time between 0 and plus infinity u, then you will recover the stationary linear Boltzmann equation for the integral over time, the integral of u over the time between 0 and plus infinity. So the existence of this integral is the reason why you have subcritical conditions.
So, Alexandre,
I finish, and then you want I finish just this slide, and then we can take a break.
right?
So
Yeah.
so now what I didn't say is that in this space every traces are well defined. So it's traces over the time 0t times gamma plus. And so it allows you to define the albedo operator, which is our measurement operator. Now your measurements are also with respect to time, and it goes to this L1 space to this L1 space. And now the question we will ask is can we recover sigma and k from A? Okay, maybe we can take a break now. This is what you wanted.
Yeah. Yeah. So any questions from the audience before we take a break?
Yeah, so I have one question.
Yes.
Yeah, so actually maybe you have mentioned this, but so are you saying like for the time means when the absorption coefficient is anisotropic, means depending on this direction, so you have better stability estimate, or
excuse me, I do not hear you well actually.
so if sigma depends on direction,
Yes.
so you have better stability estimate, or
what I say is that when sigma depends on direction, as you said, the only stability estimates that you have in general, they are here actually. You cannot do better.
Okay.
For instance, if you consider the X-ray transform,
yeah,
so if you consider the X-ray transform here, so and sigma only depends can depends on V, then you cannot recover sigma from the X-ray transform. You will always have this kind of obstruction. So let me show you the obstruction. It's really what I showed you. So you will. So if sigma depends on X and V, and you want to recover sigma from the X-ray transform, you can only recover sigma inside this class. I mean, up to this invariance here, which is given right here.
I mean in that class also you will have say Holder regularity, Holder stability.
And in that class, you will have this kind of stability. Yes.
Okay. And for the non-stationary case, so are there results when this sigma or this scattering kernel are dependent on time, or?
Can you repeat, please?
So in non-stationary case,
yes.
So what if our scattering kernel or this sigma dependent on time?
Well, if yeah, I didn't look at it, but if you add time, you certainly have the same problem as we have in the non-stationary case. Because I mean, in general, you will have the same problem as in the stationary case. Because we will use extra time variable to get more information. But if you now you put the time variable inside the k and the sigma, then you do not gain anything actually. So you will have the same trouble if you want to apply this scheme.
Okay.
I think I didn't look closely to this case, but in my opinion, you will end up with the same problem.
Okay. And one more question is that, so do you have some this single measurement results or formally determined versions of these problems?
Can you repeat?
These single measurement results or formally determined problems in this setup, like you are working with only one source or something.
No. If you allow you just one sources.
Yeah, so your albedo operator is defined only for one source.
So if you if you have only one source, well, if you for example, for X-rays, you have multiple sources. So I don't know. I don't understand your question actually. I'm sorry, but
means you are giving some data on, say, U of sigma minus, and you are defining the albedo operator from the measurements. But what I was asking, like, so what if you have only one say source, which is means you are not varying your sources in defining the albedo operator.
Yeah, but so I don't know if for example, for when you do X-ray imaging, if you have one sources, it won't be enough to recover the optical parameter sigma. So, but you're right. I mean, if you are able to consider inverse problems where you have less measurements, but
yes.
it is much better. But generally, you will have to assume more properties on what you want to recover. For example, if you want to use a finite number of sources, most probably you will have to assume that sigma and k are piecewise constant function, for example. So in that case, if you assume that sigma and k are piecewise constant function, maybe you can cook up something where you have just a finite number of sources. But be careful, because what we have proved recently with Guillaume is that in some cases different sources will produce the same data. So of course it's very specific examples, and most likely you will never encounter this kind of problem. But still, from the mathematical point of view, you have cases when two different light sources produce exactly the same external light source.
Yes.
External light measurements. Sorry.
Measurements.
So, but if you, as I said to you, it's very specific cases, and maybe you can find, if you consider constant valued function, maybe you can build things where you just need a finite number of measurements and sources.
Okay. Okay. Thank you.
Any other questions? Okay, so if not, so we will reconvene in about 45 minutes. So thanks, Alexander. So see you in about 45 minutes.
Yeah, thanks a lot.